All right, welcome to lecture here. We'll get started here in just a second. We're continuing on chapter 13, the last little bit of our organic, and I believe this is where we left off, so we'll pick up here, and then hopefully we should roll into chapter 14, which is carbohydrates after this one. Like usual, if you do have any questions, feel free to ask them at any time in the chat box, and we'll definitely make sure that we do answer your questions. So last time we talked about aldehydes, ketones, some reactions that involve them. We also got into some other organic groups and compounds like carboxylic acids. We talked about esters and how to name those guys, some reactions of those guys. And that is going to leave us right about here. And we have basically two more organic type of compounds to talk about. And both of these that are left here are basically nitrogen containing groups. So we'll get started here and start with our first one. And our first one here is an amine. And an amide is a nitrogen containing group. The functional group really of an amine is really an NH2. That NH2 is essentially based off of amines are really based off of ammonia, which is a weak base. So if you remember ammonia, you draw the Lewis structure, not into the name like I just did there. It'll look something like this: 3 hydrogens connected to the nitrogen with that lone pair. So really amines are sort of derivatives of ammonia, that NH3 group. They usually have a lot of times one less hydrogen there to allow it to sort of connect in. And again, a nitrogen with like an NH2 type group is typically what is known as an amine. Now, again, remember that the R group is an alkyl group, and essentially what that means, again, it could be something like CH3. It could be something like CH3, CH2, NH2. So again, that R is just a generic formula for some type of carbon-containing group, carbons, hydrogens connected there. Now, amines can be classified much like we classify carbons before, much like we classified alcohols before. We can classify it essentially as a primary, secondary, or tertiary amine. And for example, here, we would do kind of the same thing. We would look at the nitrogen and same idea, this R group, which is really a carbon group. And it has basically one carbon directly attached to it. And that would mean it is a primary amine. Again, just like when we did carbons, the carbon had one other carbon directly attached to it. It was a primary carbon. So this would be a primary amine. There's also secondary and tertiary amines. A secondary amine, much like what we saw with carbons and other things, will have 1 and 2 carbons attached to it. And again, that would give you your secondary amine. And our tertiary amine would have 1, 2, and really 3 carbons attached to it, would give us our tertiary amine. So the primary, secondary, and tertiary amine, the nitrogen, they do have lone pairs. Oftentimes those in condensed formulas, we don't really write them. So technically, if you had, something like this, that's oftentimes how you'll see it. In reality, there is a lone pair of electrons on that nitrogen, although again, a lot of times it is omitted sort of in the condensed formula. So you do need to know amines in terms of obviously the functional group, what makes an amine. You do need to know primary, secondary, tertiary, how to classify them. Now, because of that sort of shape that's similar to what we see with NH3, it does have a similar sort of geometry. It has 1, 2, 3, 4 electron pairs, which is our, and 3 bonds. So 4 electron pairs and 3 bonds is our trigonal pyramid shape. So again, it makes, if I didn't kind of draw it up there, it makes like that pyramid shape. And again, with those lone pairs up there, it makes kind of like a triangle kind of happening as well. So we'll have this trigonal pyramid shape, have a bond angle of 109.5, which is based off of its 4 electron pairs and its tetrahedral geometry for its electron pair geometry, not molecular geometry. Now, the amine nitrogen can also be part of a ring, as we see down here. Some drugs like morphine do contain these nitrogens in a ring type structure. Alkaloids are naturally occurring amines. And again, you see this sort of amine structure here where it sort of gets attached to this ring. And again, that's sort of common in what are known as alkaloids and morphine and those type of drugs. Now, when we go to name amines, to name a primary amine, we name the alkyl group that's bonded to the nitrogen, and then we basically just put amine at the end of it. For secondary and tertiary amines with different groups, we alphabetize the names of the alkyl groups, and if they happen to have identical groups in it, then we would call it di or tri. So if we look at this guy over here, this is a nitrogen. It is connected to 1 carbon. This would be a primary amine. And again, the kind of carbon group attached there is a methyl. So hence the name methylamine. Over here, if we look at this guy in the middle, if I could get over there, there you go. This is our nitrogen. And again, directly attached to this nitrogen is 1 carbon, 2 carbons, and 3 carbons. So this would be a tertiary amine. And each of those groups attached is a ethyl group, a 2 carbon group attached to the nitrogen. So that is where the triethyl part comes from. And amine at the end. So that is triethylamine. And lastly, we have over here a nitrogen. Get my mouth going there. A nitrogen with 2 carbons attached to it. And that would be a secondary amine. On one case, we have a 2 carbon group on the right, and that's an ethyl group. And we also have a 3 carbon group over there on the left, which is a propyl group. So again, alphabetical ethyl propyl amine. Any questions on naming those guys? Now, again, if we look at some of these here, we're going to have, this is our nitrogen attached to 1 carbon, and this would be a primary amine, even though it's long. And if we count this up here, we got 1, 2, 3, 4, 5. So that will be something like pentylamine. This again over here is a 1 and 2 carbon attached to the nitrogen, which means this is a secondary amine. We have a 2 carbon group over here, which is an ethyl. We have a 1 carbon group, which is a methyl. And again, alphabetical there, we would have ethyl, methylamine. Pentylamine is what we got over here for this first guy. And hopefully they get the same thing. And our ethyl methylamine for this guy here. Question on naming those. Now, there is another way that these guys are sometimes named, and you may sometimes come across it. And especially for secondary and tertiary amines. And because we usually will give the location of groups based on where they are on the carbon, and we would number them, you know, it's on carbon number 1, it's on carbon number 2, whatever carbon may be. In this particular case, another way that sometimes these guys are named is, if you look here, this is the longest carbon chain on either side of the nitrogen, and that's 2 carbons, which is based off of ethane. And again, you would drop the E and put ethane amine. Now, the other group is a methyl group here. That's a smaller group. And this is attached here now, not to a carbon like a normal group, but is actually attached to the nitrogen. So sometimes you'll see some people write N-methyl ethane amine, and the N means that you have a methyl group that's attached to the nitrogen, is kind of what the N means there. And then ethane amine means the longest carbon chain on the other side of the nitrogen would be basically 2. So that's another common way that secondary and tertiary amines are named. So for example, you know, this guy here, which is a little scribbly, the longest carbon chain on either side is 2. So again, the base of the name would still be that. But now what we would have is actually 2 ethyl groups attached to the nitrogen. And you know how we normally give 2 numbers? Sometimes people will do N to include that they are both attached to the nitrogen diethyl ethane amine. So you'll sometimes see these nomenclature with amines, and you'll see like these N's, and it'll go like N, or it may go N, you know, like I did on the other one there. And it may look strange to you, but it's sort of the same idea as what we do with the carbons when we number them and tell people where the groups are. Here, when we use the N, we're telling people that the alkyl group there, where did it go? This way. The alkyl group is attached to the nitrogen. So again, that's another sort of common way. That's actually more probably the IUAPC way name of it, is to use sort of the N when you're doing it for our secondary and tertiary. For our class, though, you can do secondary and tertiary, guys, just like we did here in this example. That'll be perfectly fine. But again, you should be familiar with this. This is more, again, the IUPAC way of naming it, where a lot of times people will use that N. So in case you come across it, that's what it means. The N basically means these carbon groups are attached to the nitrogens in that compound. Any questions on that there? Now, if we have an aromatic compound that contains an amine, remember that an aromatic compound is a benzene, and a benzene ring with an NH2, as we saw when we talked about benzene. That also has sort of a historical name, this whole thing. That's what's known as aniline. And again, they will sometimes do that. And here's what I was talking about with using the N. So in this case, if you take this part of the compound here, that is basically aniline, which is where the base of the name came from. And then attached to that is a 2-carbon group, which is an ethyl. And again, here, the connection is this ethyl is actually connected, let's draw a weird line, is connected to the nitrogen. So again, instead of saying carbon number 2 it's attached to, that is what the N represents, that it is attached to that nitrogen. We also could have something like we saw as well. Remember the positioning here. Again, taking this part of it, that's our aniline. This is our ethyl. And if we number, that's carbon 1, carbon 2. And 1, 2 positioning is the ortho positioning. Again, that's what the O stands for. Again, we talked about it with benzene. That's our ortho positioning. Remember, 1,3 is the meta positioning of those groups on a benzene ring, and 1,4 is the para positioning on that. Any questions on that there? So many low molecular weight amines have a very bad smell. Amines are polar, and they do have really that ability to hydrogen bond. Again, remember, in order to hydrogen bond, you need a hydrogen that's bound to either a nitrogen, oxygen, or fluorine. So in this case of the amine, obviously, we have our hydrogen that's bound to a nitrogen. So it does have the ability to hydrogen bond, which means that it is polar. That also means that it should work pretty good. Primary and secondary ones can hydrogen bond. It will work pretty good with something like water as well. They can hydrogen bond with themselves, which is going to increase the boiling point of it. Tertiary amines do not have the ability to hydrogen bond. And again, the reason tertiary amines do not have the ability to hydrogen bond is it is connected to 3 carbons, and this nitrogen has no hydrogen. So when you get to your tertiary amine, it loses that last hydrogen and thus lacks the ability to do any type of hydrogen bonding. So physical properties, whoops, come here. Physical properties of amines, they do have higher boiling points than compounds that, again, do not have the ability to hydrogen bond. So here's our ether, which again, by itself cannot hydrogen bond, as it, again, does not have a hydrogen here. And again, you can see the higher boiling point there for our amine. In comparison, though, to alcohols, for example, primary and secondary amines, although they can hydrogen bond, will still have typically a lower boiling point than alcohols. And that's because alcohols with the OH can do a stronger hydrogen bonding, because again, if you look on the periodic table, right, nitrogen, oxygen, and fluorine all in a row, electronegativity increasing this way. Thus, we have a greater separation of charge on the OH bond than the nitrogen hydrogen bond, and thus it makes it a little bit of a stronger one. Remember as well, we did finally find somebody that could beat alcohols in terms of boiling points, right? And that was our carboxylic. Don't hit the button there, come back. Our carboxylic acid. So remember, our guys that have that group attached, again, because it has the ability actually to hydrogen bond and not one location with itself, but it actually can make those dimers where it can hydrogen bond in 2 locations. And again, they have the higher boiling point. So carboxylic acid is sort of at the high end. We have our alcohols, and then again, our primary and secondary amines would have a little bit lower boiling point. Tertiary amines, which again do not have the ability to hydrogen bond because they do lack that hydrogen to do that. They typically will again have lower boiling points than primary or secondary amines of similar size. So here, that's our tertiary amine on the left. As I point to the screen, you can see me pointing, not really. On the right here, we have a secondary amine where we have our nitrogen that's attached to 2 carbons. And I'm pointing with my finger just in case you can see that. All right, so amines, they are bases, and again, they're bases because they're pretty much based off of NH3, and NH3, as you may remember, is a weak base. So amines themselves basically can act like a base, which means a base is they're going to essentially accept a proton, if you want to think about that in some cases. And a base, right, is a proton acceptor. and they will do pretty much the similar acid-base reaction in that sense, where they'll kind of pick up an H plus from something, for example, like water. The acid-base reaction occurs with all of the amines, the primary, secondary, and tertiary ones. Again, because they all have fundamentally a place for that H plus to come in, because they have these non-bonding electrons here, and that allows it to come in and bond. So amines are very weak bases compared to something that's a strong base, like we've seen before, sodium hydroxide, which is a strong base, potassium hydroxide. So these are obviously strong bases. But again, since amines are basically derivatives of ammonia, they act more on the weak base sort of side. So here's sort of your typical reaction that an amine can do. Again, it's really the same sort of proton transfer, going to end up where those non-bonding electrons are. And just like everything else, nothing changes. So we have 1, 2, and 3 CH3s, 1, 2, and 3 CH3s. We basically put on the H, and then we're left with the Cl minus. And just like our Bronsted-Lowry definition of an acid and base, we create our conjugate acid and conjugate base pairs on the other side. And again, the only difference, like we talked about then, is that they have a 1 H plus difference when it goes over. And same thing going to happen here. Again, although it may look a little bigger here, this guy is just going to plop over in your acid-base reaction. Everything on our first guy will remain exactly the same. That entire thing, exactly the same as over here. 1 and 2 H's, 1 and 2 H's, and then our third H, which is the one that came on here. And that leaves us the Cl that becomes Cl minus over here. So again, when you do any of these sort of products, or you draw in these products, or you try to figure it out, you do just want to kind of think about it the basic way. And again, don't do anything crazy. It's just going to basically look very much like the original compound. When we do this, sometimes the product is what's known as ammonium salt, because if you remember, ammonium is NH4 plus. So when this H plus comes over, it gets that plus, and it forms something that again resembles NH4 plus, which is why it's known as an ammonium salt. We're not going to do anything in terms of naming those things or anything like that, obviously. To name these ammonium salts, who cares? Good idea. All right. So just a little bit about these sort of salts as well. Again, you don't have to name them, so you don't have to worry about coming up, obviously, with this name here. But what does happen, though, in this sort of process is it goes from being water insoluble, and it's really insoluble because you have a pretty big chain of carbons there. And that big chain of carbons really does get in the way of just sort of that normal way that this guy can interact with water. But as a process of being sort of protonated, what ends up happening is you now almost have like an ionic compound. And remember, ionic compounds are pretty soluble in water. And it goes for something that is sort of insoluble in water to something that becomes sort of soluble in water because of that protonation that occurs. All right. Any questions on amines? So for amines, you need to know, again, the functional group. You need to know how to classify them as primary, secondary, tertiary. You need to know how to name primary, secondary, tertiary amines. You need to know the reaction the amine does, which is our basic acid-base reaction. And I think that's for the most part it. And now we come to what everybody, I think, has been waiting for, the very last ever here, organic group. And these are amides. And amides are also nitrogen-containing groups. The only difference is it also has that sort of carbonyl group attached. So this is the functional group. And it has this carbon-L-carbon, which is that carbon-oxygen double bond, and it kind of has an amine group attached there. And surprisingly enough, just like an amine and everything else, we could also classify amides as primary, secondary, or tertiary. And same idea here. This nitrogen is attached to one carbon, so that is a primary amide. A secondary amide would have our nitrogen here attached to one carbon here. And remember, this R group is also a carbon group. So that's two carbons, and that gives you your secondary amide. And lastly, our tertiary, one carbon group there, one carbon, and one carbon gives you your three carbon groups, which would be your tertiary amide as well. So again, very similar to how we classify everything else in terms of primary, secondary, and tertiary. So nomenclature of these guys, who cares? All right, good idea. And who cares about that? Not really feeling the naming part of it, so we're going to skip the naming part of the amide, which makes this lecture much better already. I know what you're thinking, yes. So you don't have to worry about naming amides, but you do need to be able to recognize an amide, recognize a functional group of an amide, but you won't have to name them. Let's just talk about some properties, though, of them. They do have higher boiling points, primary and secondary ones, than tertiary amides and esters. And again, it has that ability to hydrogen bond here. So here's our primary amide. It's got those hydrogens going to allow that hydrogen bonding to occur. This is our tertiary amide. Again, has 1, 2, and 3 carbons attached. No hydrogen here attached directly to the nitrogen. And again, lacks that ability to hydrogen bond. And that's sort of the same thing that we see over here with our ester. Again, our ester has the carbon-oxygen double bond with the oxygen to the carbon. Again, no real hydrogen there, so it lacks that ability to sort of hydrogen bond with each other. So again, tertiary amides are less in terms of its boiling point than primary or secondary. And again, primary and secondary having that ability to hydrogen bond. So let's talk about two reactions that these amides will undergo, and they're both what are known as hydrolysis reactions. So usually whenever you see the word hydrolysis, you should immediately think water. And water is involved, as we can see here. This is what is known as an acid catalyst, and that's what the HCl is here for, is a catalyst. Again, just to speed up the reaction, not part of the reaction or anything like that. Again, generically speaking, you may sometimes just see it written as like H plus on top, and that H plus would sort of indicate that it is a acid catalyst. So what's going to happen in this particular case is when we do it in sort of the acid catalyst, we essentially will take off the nitrogen part will come off, and it'll basically come off over here. And what will come on in its place is the OH from the water. And when the OH comes on from the water, it basically makes a carboxylic acid. And if you just sort of count up everything, you got 1 carbon, 2 carbons, 1 carbon, 2 carbons, nothing has changed. Carbon, oxygen double bond, carbon, oxygen double bond. And then the only thing that we put on there was the OH group that came from our water. Now, what's left is how we basically build the salt part of it. And if we just sort of count up everything, what came off was a nitrogen, a hydrogen and a CH3 group. So there's everybody in red, nitrogen, hydrogen, and CH group. Hydrogen from our water and the acid actually will supply an extra H just from being in the solution, and that's where these two H's basically come from. Again, one is sort of supplied by the acid that's, sort of in the solution as well. So when we do an acid hydrolysis of an amide, we will end up with a carboxylic acid and an ammonium salt. And the main thing that we'll get here again is the carboxylic acid. Now we also can do a hydrolysis reaction, which is a base hydrolysis. And in the base hydrolysis, which is why we have the base here, in the base hydrolysis, a similar sort of process occurs, except that what's going to happen is same idea. The nitrogen part's going to come off. And when it comes off, it ends up over here. And then we will pick up hydrogen with it. So this hydrogen from water will come along the way, and we will get ammonia. But slightly different in this case is the OH group is going to come on. But along the way, you're actually going to lose one of those hydrogens. And what we will actually get in this case is not a carboxylic acid, but we'll get what is known as a carboxylate ion, which is basically your carboxylic acid without the H. Yeah? And without that H, it becomes negatively charged. And this is why it's really kind of like a salt here. We have the sodium that's from the sodium hydroxide. If you're curious where that extra hydrogen sort of ended up, if you just keep track of everything that's left from the sodium hydroxide, there's an OH, and that H comes off from the OH that's going in, and these two guys will also make some water. Yeah. So like this H right here, and this OH is basically what will come together, not pictured up here, but basically water will be made sort of in this process as well. So these are two reactions that amides go through. If you do an amide and an acid hydrolysis, you will make a carboxylic acid. If you do the amide with a base hydrolysis, you will not make the completed carboxylic acid. You will actually make an anion, a negatively charged guy that basically looks exactly like the carboxylic acid, except that it's missing that hydrogen, and the oxygen ends up with a negative charge. Any questions on that there? Now, some amines and some amides. We have caffeine and nicotine. They are also nitrogen-containing groups, and they're called alkaloids. And here we can see our caffeine down here, and we have our nicotine over here. Again, we have our nitrogen-containing groups, and our amide and our amine. And that is it for this chapter. Any questions on that? So for amides, just to review, amides, you need to know the functional group of an amide, be able to recognize it as an amide. You need to be able to classify as a primary, secondary, or tertiary. You need to know basically those two reactions that if you do an acid hydrolysis, so that's water and an acid, you will generate a carboxylic acid. And if you do a base hydrolysis, you will basically generate a carboxylic acid salt, kind of like how you make soap, essentially. Any questions on any of that there? That wraps up chapter 13 in organic chemistry. We're all now professionals. There we go. All right, so we're going to roll off to chapter 14 next. Just give me a second to sort of gear that up. Pick the right one. Let's try that one. See if it likes it. It does not like it. Hang on. So picky this thing. All right, let's see. What can we do here? I think what I could do this move maybe. Let me do this real quick here. Should have some entertaining music as I'm clicking around. All right. So, all right, let's give it the old college try here again. We'll go with that one. Maybe. No, picked wrong. Still hates it. Okay, hang on. It's got to be one it likes. Let's try that one. Not very many left to choose from. All right. Found the one it liked. All right. There we go. All right, so we're in the home stretch here of chapter 14, which is carbohydrates. We got chapter 14 to go. Carbohydrates, we got lipids and proteins and amino acids, with his chapter 15 and 16. So as we go through these chapters, clearly you should pay attention, but definitely if I say it's something you should know, there's a pretty good chance it might find its way onto the final. So again, make sure you pay special attention to anything that I say. You probably should know that, okay? All right, carbohydrate. It is dinner time, so we got some bread and pasta. Can't be bad. There's people waving to us. That's a left hand, right hand. Hello. That's a good deal. So first thing we're going to talk about is something that's known as chiral compounds. And chiral compounds, it's a funky sort of symbol. Chiral compounds have the same number of atoms, but they are arranged differently in space. And they usually have one or more what is referred to as a chiral carbon. And really carbohydrates, as you may know, is made up of, choose a pen first. There we go. Carbohydrates is basically made up of carbons, hydrogens, and oxygens. So they're made up basically of those three sort of elements. And there's usually what is known as a chirocarbon. And when you look at a chirocarbon or try to identify a carbon as being chiral or not, one thing that you're looking for is it should be a carbon that has 4 different groups attached. And if it does have 4 different groups attached to that carbon, it would be considered a chirocarbon. And chiral compounds have basically mirror images that are non-superimposable. So what that means is if you take a chiral compound and you stick it in front of a mirror and you take the image that you see in the mirror out and you try to place it on the original molecule, it will not fit. So you could rotate it as much as you like. It really will never fit correctly. And that's sort of your idea with the hands, why there's hands on the screen. If you take your one hand and you put it up in front of a mirror, what you see is your other hand in the mirror. But if you pull out the mirror image, you could rotate your hand all the way around as much as you like. You will never be able to get those hands to basically sit on top of each other perfectly. You could get the thumbs pointing in the right direction, but the problem would be one is palm up and one is palm down. You cannot go palm down on both of them and get the thumbs in the right direction. You can't go palm up on both of them and get the thumbs in the right direction. So again, a chiral molecule is classified A as having a chiral carbon, which has 4 different groups attached. And if it has a chiral carbon, it's most likely a chiral molecule, which means if you take the mirror image of it, it will not be able to be superimposed upon the original molecule. And take a moment and play with your hands and see if you could get it to superimpose. You probably can't, I hope, without hurting yourself. So here are some chiral compounds that, again, cannot have a superimposable mirror image. The way, again, we could look at this guy in the middle is a carbon. And attached to this carbon is a bromine, which is different than a chlorine, which is different than a hydrogen, and that is different than an iodine. So that carbon that's in the middle has 4 different groups attached to it, and that makes it a chiral carbon, which again, if you put a mirror up, this is what will be looking back at you. And if you take that mirror image, no matter how you rotate it, You may get a couple of things like you see here to sort of match up, but you'll never get all 4 things here to correctly match up, even if you rotated any which way in 3-dimensional space. And that's sometimes very hard to sort of visualize being able to rotate. So when the mirror image is superimposable, so the opposite of sort of a chiral molecule is an achiral molecule. So an achiral molecule here is a molecule that does have a mirror image that you can take out of the mirror and you can basically superimpose on the original molecule. And one way you can identify something that's being achiral is if I look at this carbon here in the middle, it has a different group there, a different group there. But when we get over here, those 2 BRs are the same, which means we do not have 4 different groups attached. And that means that it is not a chiral molecule. It would be considered an achiral molecule. And in this particular case, this would be our mirror image. And we can rotate it in such a way that it will perfectly fit on top of the original image. So chiral molecule has a chiral carbon that contains 4 different groups, has a mirror image that will not superimpose, while an achiral molecule will have 2 groups attached to the carbon that's the same, which will give it a mirror image that is superimposable. Any questions on that? Here are some chiral and achiral molecules. We got our hands there and our gloves. We got a soccer ball, which is achiral. Right-handed scissors, I guess, is chiral. Our shoes as well are also chiral as well. So we want to look at each of these and try to determine whether or not these are chiral or achiral. So why don't you take a minute here and decide if they are chiral or achiral. All right, so again, if we're trying to determine if they're chiral or achiral, we want to look at the carbon here. And this particular carbon has a chlorine, a hydrogen, really like a methyl group, a 2-carbon group, which is an ethyl group. So that is 4 different groups attached to that carbon, which would make it a chiral compound. There we go. If we look at the middle guy in the carbon, we have a chlorine, we have a methyl group, we have 1 hydrogen, and now we have 2 hydrogens here. So this is a carbon that does not have 4 different groups attached to it. So this would be what is known as achiral. And lastly, our guy over here, this carbon has a methyl group, a bromine, a hydrogen, and a chlorine. That again is 4 different groups attached. So this guy should be chiral as well. In terms of mirror images and superimposable, these 2 guys here would then produce mirror images that are non-superimposable. This would be the only guy that his mirror image would be superimposable. Any questions on those identifications? Glad they agree. That's good. So sometimes you draw Fisher projections where we will always place the most oxidized group on top. We'll use some vertical lines and dashes to sort of represent three-dimensional space, guys coming out of the paper, guys going behind the paper. And I think we got some examples here. So again, we'll sometimes use these wedges, these kind of dotted lines as well, to indicate, you know, somebody's kind of coming out of the paper, going back in the paper. But for our purposes in the lecture, we will more often kind of draw them like this, where actually we'll just kind of use for carbohydrates really a series of intersecting lines, almost like line structure, if you will. And pretty much everywhere where those lines intersect will represent a carbon. So very much like line structure, everywhere a intersecting line sort of is, usually will represent a carbon sort of attached there. And a lot of times you'll have some OHs, some H's kind of attached. And, you know, that's sort of your general formula of a sort of carbohydrate. So we'll oftentimes use sort of that bottom sort of structure where we kind of have those guys crossing to indicate the carbons. And again, we usually don't kind of put the C's in there when we do that. We also, when we talk about carbohydrates, we'll also see D and L notations used when we name them or describing them. And D and L essentially means left and right. So D means right, L means left. And basically what we're talking about in terms of left and right is an OH group. Not just any OH group, but the OH group on the last chiral carbon. And usually that last chiral carbon is usually like right above this CH2OH group. Not 100% of the time, but a lot of times, you know, 95% of the time, if you just go up one carbon from there, that's usually the last chiral carbon. Again, it won't always be, but in a lot of cases it will be. And then the one there on the left, we do see the OH group on that one on the left. And it would be L-glyceraldehyde. While over here, we see the OH group on the right, and we would put the D notation in there. So you may ask yourself, this is a chiral carbon, is it? And it is. And just to kind of show you the chiral carbonish of it, our carbon is right here somewhere. If I find my pen, I'll just draw the carbon in. Now, attached to this carbon is this group here, which is kind of like an aldehyde, which is different than the OH group. And we do kind of consider an H a group here, so that is different. So all three of those things are different. And then on this side here, so that is 1, 2, 3, and 4 different groups attached to that carbon in the middle. And again, that's your basic definition of a chiral carbon. So you oftentimes can sort of count it like that. You find the carbon, everything above it in this type of drawing will be a group. Everything below it will be a group. To the right and left will essentially be a group. So if we look at these guys, we want to know whether or not each of these pairs is a mirror image that cannot be superimposed. All right. So if we look at the first one, we'll just start with, is it chiral or achiral? So again, if we look at this guy, this carbon, it has a group here that's different than this group, that's different than this group, and that's different than that group. So this would be chiral, which means this is a non-superimposable mirror image. And this would be like its mirror image if you kind of put the mirror right here. This would reflect here, right? This would reflect over there. That would reflect there. And then our hydrogen would reflect back that way. So those guys would be, so I guess the first answer would be yes. It's kind of worded weirdly. If we look at the bottom here, this is a group that's different than this group, and this group is different than those. But here we run into two groups that are the same. So this would then become an achiral molecule, which means you can superimpose the mirror image on this one. So if we take the mirror image, which is the one on the right, we rotate it enough, we will get it to superimpose on the original molecule. Any question on those two? So I guess yes and no is the answer on that one. So let's talk about carbohydrates, since it is sort of dinnerish. Carbohydrates is a major source of energy in our diet. We take carbohydrates in, right? They're sometimes called sugars. We use it through glycolysis in our body, right, to get some energy. And we also store some of it for later, which then could go through like gluconeogenesis. And that's all I remember from that stuff. It sounds familiar, where we could break it back down into sort of energy. Again, they're oftentimes called sugars, and basically made up of three of those elements there: carbon, hydrogen, and oxygen. They are produced through photosynthesis in plants and respiration, and we have H2O and CO2, which makes basically this nice little cycle where where we have carbohydrates and O2 as energy in this nice sort of respiration process that occurs. Now, there are some different types of carbohydrates, and we're going to talk about each of these a little bit more specifically. There are monosaccharides, mono meaning one, so they're basically a sort of simple carbohydrate. There's disaccharides, which basically consists, like the picture shows there on the bottom, of two or more monosaccharides that have basically been put together. Actually, a disaccharide would be just two of the monosaccharides. A polysaccharide is the one that actually contains many individual repeating units of monosaccharides. So monosaccharides just like one sugar, disaccharides made up of two different sugars which are connected to each other, which we'll talk about. And polysaccharides made up of a bunch of individual sugars that are also connected to each other. So let's start off by talking about monosaccharides. And monosaccharides typically are from 3 to 6 carbons. And again, we oftentimes will draw these guys like this, where we have those intersections that are occurring. Again, at each of those intersections are a carbon. And at the top, usually, or near the top, is the most oxidized type group that contains a carbonyl group. And it actually will be one of the two organic groups that we've seen, one being an aldehyde, which is this group. But a carbohydrate also could have get this out of the way here. Sorry, got something in my way. There we go. Could also have this sort of group here. And again, this is our 3 carbon run, carbon, 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 with our carbon oxygen double bond in the middle. And that is our ketone group, just like we saw in organic chemistry. So these monosaccharides will really have either a aldehyde group on top, or it will have a ketone group. And much like what we talked about in organic chemistry, those two things end up in the same location. The aldehyde group will always have to be at the top with everything connected underneath. But the ketone group will never be at the top where that carbon-oxygen double bond is, because it needs that 1, 2, 3 carbon run where we have that carbon-oxygen double bond never at the end. So it will sort of follow similarly like our organic chemistry guys will. Aldehyde group always going to be at the end. Ketone group will be, in terms of carbohydrates, usually the carbon-oxygen double bond will be one in from the end is usually where you'll find it. So they do actually have sort of special names depending on sort of what group is at the top and also how many carbons there are. So this is what is known as an aldose. And an aldose is named that because it has the aldehyde group on it. Yeah, so that makes sense. Aldehyde group is what is referred to as an aldose. And if we count this, it has, and by the way, this is always going to be like your carbon number 1 because it has a carbon-oxygen double bond. Number 2, number 3, and 4. So this is a tetrose, and that's what this name sort of refers to, an aldotetrose. Aldo meaning it has an aldehyde group on it. Tetrose meaning it has 4 carbons. Triose would have 3 carbons, pentose would have 5, and hexose would have 6 carbons. So I want you to take a second here while we're looking at this guy, and I want you to identify all of the chirocarbons there are in this particular guy. So take a minute and we'll see how you do there. See if you can identify which ones are the chirocarbons. Okay, so let's take a look here. You have 4 carbons to choose from. So we'll start at the first one. Is this a chirocarbon? So when we look at this carbon, it has 1 group attached, 2 groups attached, and only 3 groups attached, which would be everything to the bottom. So that is not a chirocarbon. Carbon number 2 has the OH group, which would be 1 group. It has the H, which would be 2 groups. Probably shouldn't do this, but I'll do it anyways. It has this entire thing up here, which is a group that's different. And it actually has this entire thing down here, which is obviously different than any other group that's there. And carbon number 2 would be a chirocarbon in that case, based on those 4 guys that I just boxed. Any questions on that? That brings us to carbon number 3. So just to kind of make it a little less busy here, we'll rebox for carbon number 3. Now, when we look at carbon number 3, it has a OH group, which is 1 group. It has a hydrogen group. And now at carbon number 3, it has that entire group, which is different than this entire group. And carbon number 3 would also be a chirocarbon in this case. And what about carbon number 4? Now, if we look at carbon number 4, and again, we'll kind of clean it up a little bit here. If we look at carbon number 4, it has this entire thing. It has an OH group attached to it. But if we were to draw it out, it technically would have one and two hydrogens that are on the same carbon, and that would make it not a chiral carbon. So in this particular case, our chiral carbons is carbon number 2 and carbon number 3. Any question on that? This also will help us determine, is this L or D? And when we're looking to determine if it's L or D, what we're looking for is the OH group on the last chiral carbon from basically the carbon-oxygen double bond. So in our case, like I mentioned before, in most cases, it is this carbon here. And when we look at that carbon, which is the last chiral carbon from the carbon-oxygen double bond, the OH group is on the right, and this would be D. Any questions on that there? Now, if we do have that ketone group attached, we can classify it a similar way. And again, you'll see here 1, 2, 3 carbon run, much like our normal thought of a ketone, with that carbon-oxygen bond happening at that second carbon right there. And that is what is referred to as a ketose. And if we count the carbons, 1, 2, 3, 4, 5, 6, that's why this is sometimes referred to as a ketohexose. It's a ketose and a hexose, has 6 carbons. This first one here, because of the 2 hydrogens, is achiral. This one right here is a chiral carbon. This one right here is a chiral carbon. And this one right here is a chiral carbon. So this particular guy has got 1, 2, 3 chiral carbons. This one here would not be chiral, again, for the same reason of those 2 hydrogens. So in terms of the D or L, which is what we're going to decide on this one right now, so hopefully this will kind of clarify your question there. Again, D means right, L means left, and what we're talking about is the OH group. And we're talking about a specific OH group. We're talking about wherever that carbon-oxygen double bond is located, which in this case is right here. We're looking for that OH group on the last chiral carbon. That last chiral carbon from the carbon-oxygen double bond. So in this particular case, each of the arrows that I circled are chiral carbons. So this carbon here is chiral, this carbon here is chiral, and this carbon here is chiral. Now, when determining D or L, we want to find the carbon-oxygen double bond, which is here. And we want to go to not the one that's closest, we want to go to the one that is the furthest carbon, that's chiral from it. And on that carbon, the OH group is attached on the right-hand side. And this would be our D in that case. So to determine D or L, you want to find first off where the carbon-oxygen double bond is. And it usually is towards the top of it when it's drawn. And then you want to find the last chiral carbon away from it. And then once you find that last chiral carbon, you want to find whichever side that OH group is, either on the left or the right. Like I said before, kind of a quick way, and again, not 100%, right? Nothing in life's 100%, but most of the time, or a lot of the time, it is usually that carbon that's like right above that last CH2OH group. So I won't say 100% of the time, but 90-ish% of the time, if you kind of go up one from that last CH2OH, that's most likely going to be the correct carbon to look at in terms of deciding you know, is it D or L? Again, not 100% of the time, but a lot of the time it will be. Other questions on that? All right, so let's take a look at these here and decide, what are we deciding? We want to know, is it an aldose, is it a ketose, and is it a triose, pentose, tetrose, or hexose? So take a moment and decide, are they aldose, ketose, and triose, tetrose, pentose, and hexose? And while you're at it, why don't you also decide, are they D or L? Okay, so looking at the first one, remember the aldose is basically your aldehyde group and your ketose is your ketone group. So that's really what you're looking for here. So again, if we sort of find that carbon oxygen double bond, we kind of highlight it, it does look like an aldehyde, which means that this should be an aldose. And then we just want to count the carbons here. So we got 1, 2, 3, 4, 5, and 6. So this should be a hexose in this case. And this would be a D because the last chiral carbon has the OH group on the right-hand side. And by the way, this guy has, in case you're counting, it has this carbon, which is chiral. So that's 1. Has this carbon, which is chiral. That's 2. This one is chiral. That's 3. And this one is chiral. That is 4. So again, here we're looking at the last chiral carbon down the road from the carbon-oxygen double bond. And again, it's on the right-hand side. Any questions on that? Now, if we look on the one on the right, we do not see the carbon-oxygen double bond at the end. We see it second in, and again, you have a 1, 2, 3 carbon run with that double bond in the middle. Again, that's your classic ketone functional group, which means this should be a ketose. We have 1, 2, 3, 4, 5 carbons, which means it would be a pentose as well. And in terms of chiral carbons in this case, it actually has 1 here and 2 here. So it only has 2 chiral carbons. And again, in this case, the OH group is on the right-hand side. So that would be your D. Any question on how to identify these guys here? Okay. And hopefully they agree. That's good. So let's talk about some of the structures, though, of some important monosaccharides. Again, a Fisher projection puts the most oxidized group on top. So that's going to be your carbon-oxygen double bond. And again, here, this is very common how we draw our carbohydrates. Any sort of intersection or where a line kind of comes across is going to represent a carbon. And that would be a chiral carbon in that case. And again, on the one on the left, the OH group is on the left, and the one on the right, the OH group is on the right, which is why the one on the left is L, and the one on the right there happens to be D. And that's what we've just been talking about. And here are some examples of some monosaccharides. And if we look at these, we could sort of classify them as well. First off, on this particular page, you need to know the name and structure of each of these guys. Yeah. So you should know these guys, their name and their structure. So put a little star next to it, put an unhappy face next to it, whatever you like to do. But you do need to know what glucose looks like. You should know what ribose looks like, and you should know what galactose looks like. So those three you will need to know. So make sure that you do know them. If we look at the glucose here, here's our glucose. This is an aldose because it has the aldehyde group on it. This ribose is also an aldose because of the aldehyde group, and so is our galactose, which is an aldose. It has 1, 2, 3, 4, 5, 6 carbons. It's a hexose. Ribose has 1, 2, 3, 4, 5 carbons. It's a pentose. And galactose has 1, 2, 3, 4, 5, 6 carbons. It is also a hexose as well. Now, again, chirocarbon, I'm just going to put like a circle. This is a chirocarbon. This is a chirocarbon. That's a chirocarbon. And that's a chirocarbon. Again, last chirocarbon, OH group on the right. This is what is known as D-glucose. And this guy here, that is chiral. That is chiral. That is chiral. Again, last chirocarbon, OH group on the right. Again, furthest away from the carbon-oxygen double bond. And over here, we got a chiral there, chiral, chiral, and chiral. Again, the last chiral carbon away from that OH, that carbon-oxygen double bond, OH group on the left-hand side, and that gives us L. Any questions on that? So again, you do need to know sort of these structures and the name to go with them. All right, so take a moment and decide, is it D or L in each of these cases? And while you're at it, the one I'm drawing up here, why don't you also decide, is it L, R, D? All right, so let's take a look. Starting on the one on the left, again, I'm just going to circle the chirocarbons, just so maybe you're counting along with me. This would be a chirocarbon, that would be a chirocarbon, and this would be our last chirocarbon in this case. Our OH is on the left-hand side, so that should be L. Coming over here, this is a chirocarbon, and this is a chirocarbon, so there's only two in this case. Again, OH group on the left-hand side, it's going to be L. And over here, that's a chirocarbon, that's a chirocarbon, and that is the last chirocarbon there. OH group on the right-hand side, so that would be D fructose. And the one I drew, this would be a chirocarbon, this would be a chirocarbon, and that last one here would not be a chirocarbon. Again, it has two hydrogens in this case, which means the last chirocarbon from the top happens to be the OH group over here on the left. So this would be L. So again, not 100% of the time is it always going to be that last one down there above the CH2OH. A lot of times it will be. But if it's not, you can then just go to the sort of second to the last one from the top there. That is chiral. Any questions on how to identify L or D or any of those type of things? And as you can also see, sometimes they have more than one chirocarbon. Sometimes they may not have any in this particular case. So looking at here, I think we will, let's see here. I think we will stop here for the moment. And this is probably a good little stopping place, actually. So we're going to stop here for the moment. So like I mentioned last time, I think what I'm going to do is we're going to take a short break, maybe a 10-minute break or so. I'm going to start back up the discussion, which again, you're welcome to come to if you can. And I'm going to continue lecturing through this chapter in hopes of probably finishing it, I think, or at least getting most of it out of the way. A couple of reminders, though. Again, I will put that recording up online in case you cannot come back for discussion. It will find its way up in the next day or so, so you can watch the rest of this chapter here. And that will technically leave us chapter 14 and 15 and 16, which should be perfect in terms of timing. Reminder that Monday we won't have lecture, so that will free up the time so you can take your exam. Our third exam, I won't say our final exam, but our third exam, our last of the midterms, I guess, will happen on Monday. Again, it will cover chapter 8, which is acid and bases. It will cover chapter 10, 11, and 12. So that's most of the organic, except for that last chapter, which I think was the one we just finished. And I'm just going off the top of my head. I think in that last chapter was it will not cover carboxylic acids, esters, amines, and amides. Now, just so we're clear, we talked about the functional group for each of those in like the very first chapter of organic chemistry that we did. So although it won't specifically cover those guys that are found in chapter 13, you still need to be able to recognize the functional group for those guys. Again, because I believe in chapter 10, we talked about everybody's functional group. So you still need to know for the exam the functional group for a carboxylic acid, an ester, an amine, and an amide, but you don't have to know anything specific like reactions, names, any of that type of stuff for this coming exam. But since we did cover kind of in chapter 10, sort of an overview of all the functional groups, those guys were part of it. So in terms of those guys, you still should know the functional groups for those guys as it could show up on the exam. But again, nothing specific from 13 other than kind of that, nothing like naming or reactions or any of those other stuff. Any questions on that? Okay, So again, I'm going to stop here. So we'll have kind of two separate recordings. If you are going to come back for the discussion, which I hope you can, uh, come through the discussion link. So not the lecture link, but come through the discussion link. And I'll start that. Let's see. We'll start about 7:20. Okay. And we'll continue on from this point. So you can get up, stretch, take a little break, and we'll continue on. All right, I'll see everybody in about 10 minutes or so if you can make it. If you're not, have a good weekend, and I'll see you next week.